Little update here on the machine. Been running this thing much of the day. This is my third bucket of water that I've gone through. The last bucket was probably up around 130 degrees until I changed it out. I've been throwing some ice bottles in here just so I don't have to change it out so much. I'm going to need a better cooling setup, but I just wanted to address some observations that I've made. Here we have, you can see that discharge off of the out of the condenser. That liquid flow you'll see there. Sometimes it'll vary. If I crank the throttling valve down on the Ebullator a little bit, you'll actually see that liquid will back up and it'll be pretty much solid instead of squirting out like that. I think it has something to do with the plumbing and the elevation it is compared to the receiver over there, that blue tank. Because whenever you crank down the throttle on this thing, it dries out a little bit and probably backs up in the receiver somewhat. Don't know exactly what the liquid level in that receiver is. I have enough refrigerant in this thing, propane that is, to fill the Ebullator up to a height of about this sight glass here. And I won't really be able to show you it because it's pretty well frosted over. It's hard to make out in the video anyway. I did finally break down and add a small computer fan just to circulate some air, which really did improve matters quite a bit. Before that, it was just a coil sitting down in the bottom, cooling, and a little aluminum can over that coil on that side, and it's getting pretty slushy, so it'll be freezing up here shortly. I cranked up the throttle a little bit. That is, I admitted a little more refrigerant, allowed the pressure to rise, but I did have this thing down to the point where a lot of that black insulation around the central column was frosted over. Got a beer in the corner there, chilling. This box is pretty piss poor. Just made out of insulation and bits and pieces that I had laying around here. So that needs to be improved. I just built that one evening after work. I was kind of in a hurry to get something out of the machine. If you're watching any of the previous videos, I have a small hermetic compressor out of an air conditioner, 5,000 BTU per hour air conditioner. It's rotary. I do need to get an amp meter on this thing. I actually have a energy detective that I could rig up with this thing on a laptop. So that's going to be really interesting, but I'll probably get into that later this week. You can see the accumulator is pretty frosted up. Frost line never gets past that point there. You can see here where this connection is brazed in for the suction. It's pretty well frosty. This large mass here, this is about where the suction temperature is taken. And speaking of the suction temperature, I thought I would demonstrate something here. Kind of neat. So we got about 19 pounds per square inch. 18.5, 19. So we refer to our table here. 18.5, 19. So we're talking somewhere between 6.5 and 8 degrees below 0 Fahrenheit. And if you observe this last value here, it's negative 3.6 degrees Fahrenheit right now. Now, something kind of fun with this, if I vary the throttle, this is my control for the throttle, it's a needle valve down inside this box. This allows me to control it from the outside without having to open up the box. I can, say for instance, if I crank it shut a little bit, see the pressure start to drop. Crank it a little more so it goes a little faster. So what's happening is the compressor is actually drawing off vapor just as it was before, but less refrigerant is being emitted from the high side, so the pressure drops. So I have to tweak or play with it a little bit. It's very, very sensitive. Needle valve is a bit of a misnomer. It really doesn't have a needle in it. Needle control. It's a flat piece of machined steel. Whoops. So I'll let that thing even out a little bit and talk about the high side here. We're running pretty hot. This is a just water cooled heat exchanger here on the condenser. It's like 25 feet, 1/4 inch copper tubing. We're at about 180 pounds per square inch on the high side. Again, if we refer to our chart, assuming this is for R290 pure propane, what I have in this system here is actually barbecue grade. So what did I say, 190, which is 106.4 degrees Fahrenheit. Now this temperature here on the top, 107.2, that's taken from a thermocouple directly on the surface, almost directly on the surface. There's some insulating tape, electrically insulated tape between it and the copper tubing coming out of the compressor. A little bit of insulation around it to get a little better reading. But I think it is interesting that that value so closely corresponds to the condensing temperature at that pressure. And through various conditions all day long, I've seen temperatures as high as 138 degrees, actually 140 at one point on the high side, and it very, very closely corresponds to the pressure associated with that temperature. So it's pretty neat to see that close correlation. Is that an accurate number? Well, I'm sure it's not, but to see it track so well, all is within 1 to, I'd say, 4 degrees above what the corresponding condenser pressure or condenser temperature is at that pressure. So let this stabilize a little bit, and on the suction side, you see it's about -10 pounds per square inch, which corresponds to -21 degrees Fahrenheit. And you see our suction temperature, back pressure temperature, whatever you want to call it, -15 degrees Fahrenheit. Now at these lower pressures and lower corresponding temperatures, the number doesn't track so well. One of the reasons for that, the long suction tube, such a low temperature, isn't going to probably read as well. The copper tubing is going to rise in temperature even through this insulation here, but at suction pressures and temperatures above zero, it's almost always within 2 or 3 degrees. -17, what did I say? 9, -23. So yeah, so you're talking, 5, 6 degrees in superheat, if that number is to be trusted. And most people would tell you that that's perfectly reasonable for superheat. And what's cool about this thing is that I don't have any control for superheat. That's not the way this thing is regulated. It's regulated by really, in some ways, very naturally. It's regulated by the throttle, which I operate myself, and but the heat load within the box, the high side pressure, the liquid being admitted to it, and the compressor, all those things together dictate what the temperature of the coil is going to be. But the superheat is almost always going to be, if not dead on to the associated temperature at the suction pressure, it's going to be just a few degrees higher, no matter where I set this throttle at. And the reason for that is because this isn't a gravity-flooded evaporator. The suction gas being taken back to the compressor is always near saturation. And the reason for that is the fact that the evaporator is always in a flooded condition. I mean, it's a flooded evaporator. A dry evaporator, the type where you see it has all the coils with a TXV, the TXV regulates the amount of refrigerant going into the coil based on the amount of superheat being produced. If you were to flood the thing, you could actually have liquid refrigerant going back to the compressor, which is a very bad thing. On the other hand, if it didn't admit enough refrigerant, it's going to dry out. Now, the same thing can happen with this thing. If I crank this thing down, I mean, even at this low pressure, I can't demonstrate it for you on the sight glass very well, but it is going to dry this thing out a little bit. The liquid level is going to drop because more refrigerant is being carried away to the compressor. What I was surprised to find was that above zero, above about 10 degrees Fahrenheit, just about any point at which I would adjust this throttle, I would see the liquid level more or less be maintained right around the height of that sight glass. And I said I was a little bit surprised to see that, but on the other hand, there might be a perfectly good reason for it. At those lower temperatures, lower pressures and temperatures associated with it, there's a hell of a lot more of a delta T temperature difference, that is, between the evaporator coil and the contents of the box, whether it is cooling beer, or cooling the air, whatever it happens to be. And when there's a larger temperature difference, the ebullition, the boiling, that is, of the propane refrigerant inside the coils will occur at in a more violent manner. and that refrigerant, as it boils over, comes up the coils themselves and carries liquid out over. Even though it might be in somewhat of a dry condition, the liquid level that's maintained, even though there's a lower volume of lower mass of actual liquid within the coils themselves, the activity continues to be maintained. And at these really low pressures, I actually start to see if I can actually see it. I can't even make it out. No, I don't really see anything in there other than a little bit of turbulent vapor. So it is in a little bit of a dry condition. Now, ideally, and I can run this thing in such a condition that I open the throttle up a little bit, allowing the pressure to rise up quite a bit, and it'll actually get to the point where I can maintain that liquid level in there and adjust the throttling valve every 10 minutes or so just to keep it there. But the suction temperature associated with the pressure will be maybe just a few degrees lower than the contents of the box. Right now, this temperature here is just the air temperature. There's just a probe hanging down there. I don't know how accurate it is, but it's pretty damn cold in there. The other cool thing about the flooded evaporator is that the delta T, say, rule of thumb might be 10 degrees temperature difference between the coil and the medium that you're cooling. Say it's a cooler or refrigerator or something, in order to get enough heat transfer across it. The other thing that's kind of maintained naturally with this system is if you're maintaining a liquid at a certain level, say by me, the actual operator, adjusting it, or a liquid float that admits more refrigerant as it drops, and then shuts it off whenever it rises up enough. In that condition, the delta T is self-selected. It's naturally found based on the surface area of the copper coils, the heat carrying capacity of the refrigerant, the heat conductivity of the copper itself, the humidity in the air. All these factors come into play, which essentially allow the delta T to be maintained at, it might be 4 degrees Fahrenheit, it might be 10, it might be 15, whatever it is. If I add more surface area, or in this case actually add a fan like I did, I can actually increase or decrease the heat load. And again, the delta T is more or less maintained. Now, the reason I'm running at such a low temperature right now, there's a little can in there that I'm freezing, is because if I just maintain this at a certain liquid level, the delta T will be relatively small, and which theoretically would be a good thing. If I continually match the liquid level and allow the temperature inside the box to drop, and the water can to drop, and the beer bottle to drop, and everything like that, the liquid level would theoretically begin to rise as the delta T got smaller, the heat transfer decrease, less ebullition, less vapor being produced, which would slowly allow the pressure to rise. In which case, I might crank the throttling valve a little bit down, which would decrease the pressure, decrease the amount of liquid, and the liquid gradually falls. It's being carried away. As the pressure drops, the heat transfer increases, the delta T increases, and the load is maintained. Now, the problem with doing that, and I've found this out, is that, well, this box is perfect. I mean, it's not insulated very well. It's 80 degrees outside right now. So, the heat being pulled into the box, the heat being conducted into the box, might overcome the ability of the system to carry it away, and it actually might even get to the point where it just matches at a particular setting on the throttle. What I found myself doing was actually cranking it down a little bit to lower the pressure, increase the delta T, so it carries it away faster. Ideally, the way that I see it is that if you wanted the most efficient operation and you wanted to cool something down as efficiently as possible, you want the smallest delta T. The reason being, you want the evaporator pressure to be as high as possible in order to admit the highest suction pressure to the compressor, so it's less work that it has to do. A smaller compression ratio, for instance, and a more dense gas vapor being pulled back to the compressor. So anyway, there's a lot of things that I want to continue playing with, but I am having some fun with this little rotary. This kind of kicks ass. The only issue with it is the fact that I can't really vary the compressor speed, of course. So, one of the next things I'm going to do is throw the TED on there, the energy detective, and monitor the amperage draw on the compressor in various conditions, and continue playing around with the box a little bit. Now the box is going to get changed eventually. This thing's an ugly piece of shit, and the entire Ebullator, I'm going to build a new one, one that actually chills, makes plate ice, because there are also some issues. I mean, there's poor surface area in here. The fan helped substantially, but I don't like the fact that there's such long runs of coil in there. So the next Ebullator is actually going to have pretty much vertical coils. You get a lot more brazing, but good heat transfer to make ice. And eventually, I think I might get a refrigerator, cut some holes in it, modify it quite a bit, and take some evaporator coils, condenser coils, either way, it doesn't matter, heat exchanger, air heat exchanger coils, and modify and make them into flooded systems. And eventually I'm going to fool around with some TXVs and see if I can modify a TXV to actually operate as a kind of a makeshift float, liquid level control, thermostatic liquid level control, if you will. So that's going to be a little ways down the road, but in the meantime, I'm going to finish this thing till it freezes solid. See if my beer's good and chilled yet. Anyway, have a great day.